Well, hello everyone. Matthias from Archilyse will be telling us about the missing link, optimization approaches in generative design. So take it away, Matthias.
Hey, thanks for the intro. Hi, everybody. Great of you to join us. I will deactivate my video so I don't get too distracted. Um, Regarding my person, I'm Matthias. I'm CEO and founder of Archilyse. So we are one of Europe's prop tech startups. So you will find more information on our webpage, www.archilyse.com. I will shortly introduce what we are doing, but before I go into our company, just 2 cents regarding my person. I have a background in architecture, but I did my PhD in machine learning at ETH in Zurich. I also have a background in mechanical engineering and philosophy, and in between I did lots of coding and data science. So I'm more this hands-on hacker person. So also out of this respect, I'm going to keep everything a little bit more informal, and I hope this is fun for you. So just a short overview of what my company is doing. So we work for large-scale real estate developers and asset managers, and we have our unique workflow of automatically converting their floor plan archives, mainly 2D hard copies, into RFC files. So this is one of those RFC files. As you see, we use RFC OpenShell to render it online. And we hand all this information then, get into it later, in our own document management system. So this is what we do. We do data enrichment, data refinery, and data structuralization. So we do this by, on the one hand, converting everything into a 3D model, and in a second step, putting the 3D model into a 3D model of its environment. So we have most of Europe covered. Out of this fusion of geometries, we then can do simulations. So we have our own simulation engines for natural light, 3D view, isolists, for centrality metrics, certain kinds of functionality, certain standards our customers need to comply with, and of course this generic building masses and floor masses and so on. And in a subsequent last step, we then use the generated standardized features, and we correlate it with rent revenues, building costs, energy consumptions, CO2 emissions, and work with well-established valuation agencies on the European market, and are like a kicker for AVMs, meaning automated valuation models. My personal vision is that in the near future, the whole architecture competition sphere is going to turn more like into some kind of kegel for architects, where you have immediate, real-time live feedback on your designs and how you are performing in the different architecture competitions, giving you a chance to retract early enough so you can save costs. On the other hand, to go the extra mile to win an architecture competition. So this is more or less the big context of Archilyse and where we are coming from. But for today's meeting, we're talking about something different, or something much more detailed and much more technical. So, I think the audience here knows Grasshopper, knows Galapagos, and has a rough understanding of the different components you can work with in order to do building hull or building optimisations. And those are easy to apply genetic algorithms. I think most of us have used them, most of us know how they are working, and I think most of us know the pitfalls, either from a more hands-on perspective or from a more scientific perspective, because like the video I've shown you here is from Decoding Spaces. This is a group of Weimar / the Future Cities Lab in Singapore I was working with for some time, and it's the same stuff. So you're working on multi-criteria optimization, genetic algorithms, and in this case, we have developed this small part of Singapore with all the simulations you anyhow might know, like visibility, shadowing, sunlights, and then out of this, generating a Pareto front of designs. Obviously, this stuff is more or less easy to do. And what we are facing at the moment is like this cascade of new startups within this domain popping up. There are lots of startups you might know, there are others less known. I mean, I think the most prominent one was Spacemaker, which was acquired by AboutArchilyse, but there are other promising or less known startups doing more or less the same thing. I mean, what we're doing here is you have a building lot and you want to generate a so-called optimal design, and you're going to do site solving, or you solve this problem for real estate developers. And this is now, I think, where everything gets a little fussy, because to be honest, I think so straightforward as everybody's saying, as everybody is at least mimicking the process, it's sadly not. I mean, the moment when we are talking now about an optimal architecture design, we are talking about so many pitfalls some of us might have already stumbled into. I think the most prominent one is the Pareto front. I mean, the moment you use genetic algorithms or multi-criteria optimizations, you face a Pareto front problem at a certain point. If you have two or more dimensions or two or more parameters, where the moment you increase one, another one is going to decrease, you are facing this Pareto front issue, because you are facing something you cannot optimize any further. So state of the art at the moment is that with all of these genetic algorithms, in the end, you're generating the optimal combinations of parameters for different situations. And then you design a solution space, and you propose the designer a set of possibilities he then can later pick off, where in your design algorithm or in your design engine, from your understanding of the matter or from the inputs you got, all solutions are similarly good or bad. So what we have learned from genetic algorithms or from design itself is the more iterations you put into, the better the results become. So you start with more or less bad designs, randomly chosen parameters, and then with the final population or the intermediate population, you get closer and closer to this Pareto front. And this is what the solution space, this complex interaction of parameters, is allowing you in your design. And then you're facing those trade-offs, and you need to pick a choice in the end. This is the problem in architecture. When you do an architecture competition, there's always a winner. And what we are saying now, what is the state of the art is telling us, is that in this genetic algorithms, you should design some human-in-the-loop interface, where the architect or the designer can still more or less pick his winner, has some subjective input in an otherwise highly objective process, and can generate more or less a drift. So in the end, you have this final design as an interaction, as a result of the interaction between designer and algorithm. And this is a nice story, but it is really what our technology should be used for. I mean, this is maybe my hardcore mechanical approach to this topic, but I think this Pareto front is overly stretched, and I'm not a big fan of it, especially since reality in architecture competition tells us there is always a single winner. In all of those architecture competitions, you always have one design in the end. And the hypothesis we are working on is that the Pareto front itself is a result of a lack of information and context. Because when you, for example, need either to optimize in regards of building costs or of expected revenues, you lose the big picture, because maybe the most efficient way would be to optimize in regards of discounted cash flow or the yield you could generate with your real estate in the end. And this is how asset managers and real estate developers are approaching this whole topic. So they have this one single number. They have this one idea that with your discounted cash flow, in the end, in the box, this is the one metric you are measuring architecture against. And this is where we are coming from. So when we are going back to this idea of having this more or less feedback loop, this is something you know from mechanical engineering, um, in other domains for ages now, is that you go a little further left and you go a little further right. You approach a target with a so-called gradient descent. So take the moment when you start learning to throw darts on a dartboard. So you throw you understand that you should hit the bullseye, and after you understand you should hit the bullseye, you start throwing the first dart, and you're to left. So the next time your goal is to hit the board for the right, and you aim for the right, and then it may be too right. So you try to approach this target on a more or less good resilient way. So in the end, after training, after lots of exercise, you want to be able to hit the bullseye every time you want to hit it. The thing is, if you play darts, bullseye might not be the best place or the best space of the board to hit. I mean, you would start with the triple 20, as everybody in a pub could tell you. So now we have two issues. So first, we have the accuracy. The accuracy is the thing, how well are you able to throw the dart? And the bias is, how well do you understand the game, more or less? Do you know whether to hit the bullseye or the triple 20? And this is the same thing what we do in architecture design. So you know that you go over your designs iteratively. You change certain parameters, you go further left, further right, you increase or decrease something, and you approach a target. And as a designer, as an architect, you have your bullseye in mind, maybe. So your bullseye might be increasing the volume you can build on a site, while at the same time reducing shadows, increasing sun exposure, maybe increasing the view, whatever you can think of else. But in the end, the triple 20 you're missing could be, for example, the discounted cash flow, or in a bigger picture, it could be CO2 emissions. But there is always this triple 20 we are missing when playing darts or when designing architecture. So there is this one question, is how do we define our fitness parameter? Where should we hit the dartboard? And this is now quite philosophical, because the question is, what is truly good? And there are many ways to approach this. There are the ways of a more a posteriori, there is of a more data-driven basis, and there are ways of a more rule-based strategy. And what I can tell you already is that the issue with this whole strategy is that it's really hard to tell which effects are hidden in a design when you're not considering the full picture, when you are not considering all the dimensions, all the potential simulations or behaviors at stake when you change a design. I mean, the moment you increase one building, you might also decrease the sun exposure of another. The moment you increase one volume, you might decrease the noise exposure of another. So everything is more or less connected. And in order to get the full idea, you need to simulate everything. You need to simulate the shit out of it. This is how I phrase it usually. And when we are now talking about fitness functions in detail, we found out that there are many more abstract fitness functions, like discounted cash flow, or, for example, number of potential publications for an architectural designer, which mimic reality much closer. And in order to approach those fitness functions, a purely rule-based approach is not valid or useful anymore. So this is the moment we need to go from generative design to data analysis, to machine learning, to looking into historic data in order to understand what's really good or what we want to approach and what we want to achieve with our design. Because in the end, when we look into neural networks, when we look into machine learning, we soon find something called a stochastic gradient descent. This is the approach how you can, in a robust way, detect a global optimum, and how you can continuously approach this global optimum. And this is another approach compared to genetic algorithms of optimization, so to speak. And this is also an approach I'm prolonging in architecture. I mean, I strongly believe that if you can understand the design domain or the design issue at hand properly, you could apply a stochastic gradient descent in order to solve your design issue rather than simply using a genetic algorithm to generate lots of crazy looking designs. Because the value of numeric, of data-driven or of digital design processes, the value is not in generating an abundance of designs. The value is in generating better designs. And I think this is something we are at the moment in a stage in our tech environment where we need to be reminded that this is the issue we should look into. And for example, the historic design process with its architecture competitions is exactly designed in this way of stochastic gradient descent. And if you follow such a path of a stochastic gradient descent design evolution, you will find out that most of the designs are evolving anyhow on a more gradual level. So there is never there's never a non-linear design development. All designs are more or less follow-ups. And my most favorite example, because I don't like Apple, is Steve Jobs did not invent smartphones. Design is never ex nihilo. So design is always based on something previously. And with the previously designed something, you were able to collect experience, you were able to do tests, and then you could derive the path in a stochastic gradient descent. If we look into adjacent domains, when we're talking about machine learning, when we're talking about optimization, when we're talking about everything that is data-driven nowadays, there are a few examples. I think one of the easiest examples is self-driving cars. There's this one thing most of us tend to forget, is that self-driving cars, as Tesla is pushing it at the moment, is crazy. It is still crazy because back in 2004, DARPA from the US Air Force pushed one of the first challenges where like cutting-edge machine learning teams were invited to have their own crazy vehicles drive through the Mojave Desert and approach a goal, and approach a target, an objective whatsoever. So in 2004, none of these cars were able to finish the route. There were no winners. Everybody lost because the task was too complex. The algorithms weren't there. The understanding of the material at hand was not there. And nowadays, self-driving almost becomes a commodity. And this is within more or less 15 years, we were not able to perceive a full paradigm shift in something people were steering, humans were steering, to something humans are consuming. And what we have in architecture design is more or less the same thing. It's in a different time scale, of course, but we are part of a paradigm shift at the moment as we speak. Another example, same time span, is on the left-hand side, you see from 2004, a humanoid robot of Honda, which was not able to climb upstairs. On the right-hand side, you see a Boston Dynamics robot from 2020. Within 15 years, they have revolutionized this game, and it was only able because we changed the paradigms. Those tools learned, and the algorithms were working. So that the concept underneath is that we went away from rule-based designs rather to data-driven designs. And Nowadays, even one step further, we are talking about reinforcement learning. So there are tutorials out on the market, and you can see it everywhere. I mean, the idea is that now the algorithm you can easily code is testing the assumptions in his own more or less synthetic environment. And the algorithm can learn how to drive much faster, much more resilient than what Tesla did ages ago. So this is, even those reinforcement learning tools are now becoming a commodity. But again, the issue is how can you steer it, and how can you generate such a behavior? How can you work with your optimization methods in such a way? The moment you generate, you design something parametrically, is it Grasshopper? Is it Dynamo? Is it anything else? The moment you describe something in numbers, you open the door to optimization methods. So everything you design parametrically is going to be optimized eventually. And this is the big risk, because if you are not properly defining the targets of these optimizations, you're not hitting the bullseye, you're not hitting the triple 20, you might hit something totally different. And as I said before, that the critical point here is you need to understand which kinds of knowledge you're using. Is it rule-based or is it data-based fitness criteria? Rule-based is everything that is predefined mathematically. Rule-based is everything you might know already, because we as humans need to verbalize rules in order to communicate with each other. When we are talking about concepts, when we are talking about how we understand the world, how we should behave, we are not talking in raw data. We are not talking in our experiences in detail and let others come to similar conclusions. What we do in order to save time, in order to reduce the redundancies in our communications, is we talk about concepts, we talk about similarities, we talk about rules. And we have developed our own design, our own science, in order to derive rules from observations. So rules are not intrinsically bad, but rules are something always filtered by humans and human understandings. When we're talking about rule-based fitness criteria, we assume that the full behavior of a fitness can be deterministically predefined. Means that everything we consider as important can be put into mathematical formulas. Could be the case, but it mustn't be the case. I mean, it doesn't have to be the case. It's just potential. It is a potential way of many. And there are different scientific domains where this is more or less used or applicable. I mean, of course, it is in math, but you might also, if you work in the domain of religion, everything there is purely rule-based and axiomatic. There might also be the issue with medicine. So there are parts of medicine where you do your studies, you do your data-driven setups, you do different studies, then you do meta studies, and you generate something that's more or less an objective or an intersubjective knowledge. And out of these findings, you then generate rules. You say that under this and that condition, you need to do this and that. And for centuries, this rule-based approach was the dominant paradigm in science as well as in machine learning. I mean, if you read Gödel Escher back from the 80s, it's the same thing. So when the author is talking about machine learning, he's only talking about rules. He's only talking about causality, correlation, and how stuff needs to interact. And when you read how Noam Chomsky is describing his language models, everything there is more or less rule-based itself. And when you translate this into state-of-the-art, more state-of-the-art machine learning stuff, you will land at IBM Watson. I mean, maybe some of you have heard of IBM Watson. IBM Watson is this It's now a B2B service IBM is selling, but the big poster case was that they had an AI, which was more or less suggesting a set, a mix of chemicals for chemotherapy for oncologists. So the idea is you had all of these parameters, like you have in Christopher. You were moving certain blood values, you were moving certain other criteria of the patient, and then IBM Watson came up with the perfect cocktail of chemotherapy pills. The very sad thing is it didn't work out as it should have, and you will find articles about this topic online, but it was not successful because the IBM was using all of these medical journals, medical papers, drawing certain connections. So what IBM Watson was doing was more or less an NLP approach. So natural language processing of all of the medical papers out there. And IBM Watson was more or less mimicking state-of-the-art medical knowledge or oncological knowledge. And when you now came with a task to this IBM Watson guy for oncology, he was giving you the feedback, the common sense of all the oncologists in the pipeline. And since everything was statistically normalized, it was not as sharp. It was a little fuzzy. It was like a JPEG with a low resolution. This was bad. On the other hand, now, since recently, we have a data-based approach. So not rule-based, but data-based. The Latin terms are, for this would now be a posteriori knowledge. Rule-based would be a priori knowledge. So in this data-based approach, all the behavior of your algorithms would be defined or derived from observations. So the thing is now, in a data-based approach, you do not need to define rules. In a data-based approach, the rules are being defined on the fly. So it's like you yourself, with the ability to collect all the experiences of all the designers or all the oncologists out there in your own lifetime, which was, of course, would be impossible. But this is more or less the way you need to think of those data-driven approaches. So a machine learning approach has access to much more raw data. And because it has access to such an amount of raw data, it can conclude more nuanced knowledge. It can conclude more nuanced rules underneath. And it's like a JPEG with much higher resolution. And you have applications for those data-based approaches nowadays everywhere. I mean, you're talking about physics, chemistry, medicine, and so on. And everything that's more or less based upon science, based upon studies, collecting data in order to derive knowledge on the fly. I mean, to come back to our previous examples. So since recently the dominant paradigm for decision making, compared to Noam Chomsky, nowadays we have GPT-3 as a much more sophisticated, computerized or digitized model of language. And compared to IBM Watson, you might have this Google DeepMind application for skin cancer detecting. So what Google DeepMind did is they had access to thousands and millions of pictures of skin cancer, of healthy, of bad tissues, and so on. And they were training an algorithm, and then they were peer reviewing this algorithm. And since it's purely data-driven and it's not based upon human knowledge, but it's really based upon the raw data itself, it's outperforming dermatologists. It is a good approach of digital tools. And I think this is now the threshold in which we are working on. I wanted to show you a video, but I simply can't get the noise running. I mean, you can look it up later on your own. There is this Google Duplex AI Assistant. It was a big thing back in 2018, but there were certain privacy issues, so they didn't launch it back then. Essentially, they had a robot calling hairdressers, bars, pubs, restaurants, whatever, and the robot was doing the appointments for you in the back while you were using your Google Assistant on your phone. And the language models there are so sophisticated, they mimic a human one-to-one. And this would not have been possible with rule-based approaches. This is only possible because of data-driven approaches. So, and we are now doing a similar thing in architecture. When we are working with volumetric optimizers, what we are doing is essentially we are doing a deterministic rule-based approach. We are telling our machine, we are telling our algorithms that we are predefining a best fit. And we are predefining this best fit with the stuff we know from literature, from science. I mean, I'm coming to an example of these topics in a few seconds. And this is dangerous because this is more or less the experience of other people, and it's going to be outdated very soon. Because the big risk of those rule-based approaches, because they are so slow, because there is a scientific feedback loop behind it. Now, with a changing environment, with a changing economic and ecological environment due to climate crisis, most of the experience we are facing in literature or our peers have is not worth anything anymore. I mean, we need to rethink the world much more drastically. And to do this, you need to have different fitness parameters. You need to be able to push boundaries much faster. But in order to do so, you need to also have better understanding of the KPIs you're using, and you need to have KPIs of other stakeholders involved. So, as I said before, it could be either the discounted cash flow, or it could be CO2 emissions. It could be gray energy, or it could be virtual water. It could simply be the land use, or it could be COVID exposure. I mean, there are so many factors nowadays affecting architecture that it's really hard to differ the good from the bad. And I'm not giving you an answer. It's just that I want to make awareness that this is an issue we are currently facing in architecture. So when we are talking about this rule-based approaches, we need to know that at the moment, this is how our whole society, our whole technology works. I mean, let's take space syntax. I think hopefully everybody here who's working in design knows space syntax. It's Bill Hillier, Space is the Machine. It was a very breakthrough publication back in the mid-90s at UCL. And what this guy did is he came up with a simulation analyzing your field of view or your view shed and so-called isoist metrics and certain graph metrics. And he was more or less able to predict the pedestrian flow in buildings or in the built environment. Back then, everything was limited due to computation power. So it was two-dimensional, it had certain trade-offs and so on. So what we did back at ETH was then we put it into a third dimension. So you had three-dimensional isoists, you had much more information underneath, and then we were not only counting the pedestrian flow, but we were measuring the biofeedback. So in certain situations, you now were able to measure, is there certain arousal or is there stress relief within the test subjects or the pedestrians walking around. And so you had a much more data-driven model and that much more data-driven understanding of space itself. Where would you feel more comfortable? Where would you find your ways easier? So there are numeric models underneath, and this is done by space. But as I said, this is very slow. But again, this is also driven by machine learning. And another nice example when we talk about data-driven designs is the British bombers of World War II. I mean, a few of you might know this example. This is the so-called survivorship bias. Is the planes came back from Nazi Germany, and all those red dots in the plane resemble the hole from a bullet. So the engineers were working on it, and they tried to enforce exactly those areas where they had lots of bullet holes, because they thought, well, this would be important. I mean, this is where the people are, the Nazis are hitting us, so we need to defend ourselves. And then there was this one smart statistician who said, hey, guys, this is bullshit. Those planes with the bullet holes at these places, those planes are coming back. We need to enforce exactly where we do not see any bullet holes, because planes with bullet holes at those places, they are not coming back from Nazi Germany. And this is the way you can work with data to improve your fitness function. And it's maybe a little abstract version, but it's more or less the way we should tackle this whole problem. We need to foster an environment where we see every building, every design, which is built as an experiment. And we need to have a workflow where we need to gather data from those experiments and extrapolate knowledge from there in order to make future designs more resilient or better. And this is why our company, I mean, my company in this case, Archilyse, where our main focus is on generating digital twins or RFC files from existing buildings, from asset managers. I mean, so we have a proper data set, so we can derive knowledge from in order to improve, to inform the decisions from real estate developers, at least in our target countries. And this is also the backbone of our whole industrialized revolution from the early 19th century. There's this one smart guy, Joseph Whitworth, and if you ever visit CERN, you might find this quote written over the fabric hall where they built the components for the superconductors. And he said that you can only make as well as you can measure. And of course, I mean, in CERN, you measure particles, but the whole idea is that these fitness parameters are really informing the way we are designing. They are not something abstract we need to use as a tool in order to have better informed decisions. The fitness parameter itself is the most important decision we as a designer do. So this fitness parameter is something we need to shed much more light on, rather than which shape grammar we are using. And in order to do so, I mean, at the moment on the market, you're facing certain so-called need metrics. I mean, in the lower left quadrant, you see expressed needs in this metrics. And this means that you in your current company, in the discussions with your customers, you work on certain expressed needs. And the most prominent expressed need is, please automatize this process for me. And it's a nice need. I mean, we are doing optimization all the time, but this is only what the client is currently aware of. Then there are few clients who are aware of their future need, and their future need is going to be, hey, please set up a proper process, because we are going to need to work with AI soon. I mean, within the next at least 10 years, there has to be a resilient AI process in our company. And I'm talking to those large-scale real estate developers or asset managers with tens of billions under management. And this is their issue. They know that this is going to disrupt the market. They simply do not know how. And because there are unaware needs. The customer does not know what he's needing at the moment, and he knows even less of what he's going to need in future. And this latent need at the moment is data homogenization. And this is now why I'm such a big fan of speccing. Because data homogenization means you need to have like a standard. This is what IFC should have been, but it's not, because IFC is a little complicated in my opinion. You can work on a much lower granularity here. So with Speckle, we can start data homogenization. We can have an interface everybody of us in our domain can work with. And this is also something we are going to need in future anyhow. But then there's this emerging need nobody is aware of at the moment. This emerging need is data densification. And there are amazing simulation tools out there on the market for Grasshopper. I think some of those guys are even attending today. And with all of the simulation, so I always say science the shit out of architecture. With all of the simulations you have, we can densify the solution space. We can densify the data we are working with, the designs. We need to know what is the view condition of existing buildings, what is the sunlight, how do people feel. But we need to also aggregate more information here. We need to aggregate what is the tenant fluctuation, what are the market prices, what is the energy consumption. There are nice studies showing that there's a strong correlation between micro apartments and domestic violence. There are nice studies showing that there's a strong correlation between the cognitive capacity of children and the natural light they have in their bedroom. There are scientific studies establishing a strong correlation between how long you need in order to recover in a hospital and the amount of sky you see from your bed. There are strong correlations for almost everything, so like migraine. I mean, the more greenery you see when you look out of your window, the less migraine you're going to suffer. So there's so much information out there in the market we simply need to collect in order to really do a proper fitness function for architecture. So it is, what I'm talking about here is turning architecture into a proper engineering science rather than just an artistic experience of generating thousands of designs nobody's ever building anyhow. And our responsibility as tech provider, as the tech savvy people in this domain is to work with those kinds of push and pull innovations. So we need to show them how to have proper digitization workflows, how to do quality benchmarks. So there are certain elements, some startups of us are anyhow working on. And then in order to come to a proper conclusion, I think, on where this fitness function needs to come from, we need to consider how we are able at the moment to compare architecture. And I found this meme on Imgur, one of my most favorite sites, a few weeks ago. And I really like this because this is our current state of data analytics and feature design in architecture itself. So we are using meaningless criteria in order to describe architecture. And these meaningless criteria not only introduce certain bias, but they also introduce a certain drift, leading us to suboptimal designs. So as long as we are not collecting the proper data, as long as we are not building our knowledge on top of proper existing experiments, we are failing with our optimization algorithms, independent if we're using genetic algorithms or stochastic gradient descent. So just five bullet points in this to this topic. I mean, most importantly is we need to go away from discrete data. So we need to work with continuous data frames. We need to work with dense data spaces. So not sporadic ones, but dense is meaning that data points we can gather for every building. So we should not look into the exotic stuff. We should not look into this exotic buildings in order to make the world a better place. We need to work with this more or less profane buildings like housing, office, the generic stuff. And we need to look into the significance of this information. There's this in language models, term frequency, inverse document frequency, the GFIDF. And there are similar approaches here in architecture too. So there is a way to qualify and quantify the value of certain information. And this is what we need to look into. And everything needs to be understandable. There is this big narrative now of explainable AI. And some of the valuation providers at the moment are already working on it. So this is where it's going, where it's going to end up in a few years. And now this is my last slide before we can start with the questions. And I hope there are a few. So when we look at the current trend in our domain, we, for example, see that investors and manufacturers in their communication and in their whole deal flow go much further together. So the resulting freedom for architects and planners is reduced, and we can have the best tools. But we need, if you're not able to speak either the language of investors or the language of manufacturers, we are going to end up stranded. I mean, of course, what architecture is doing, I mean, we are now working much more with the manufacturing language. So we started with 3D printing, robots, and milling machines, and so on. What we have failed so far is to come up with tools, numbers, KPIs, and a language of the more financial part on the top of the value chain, because this is where we need to attack in order to expand, in order to make to have a resilient stance. And this is why we need to close the gap between architectural qualities and certain financial, social, economic, or economic KPIs. When ESG, what everybody's talking about now here in the European Union, is only one thing, but there are so many more important features we would need to consider in order to have more meaningful designs and to be much more successful with our design algorithms. We need to consider that at a certain point, architectural quality itself becomes a metric, an objective metric. It's like when we're working on vaccinations. I mean, you know which vaccines are working well and which don't, and architecture is going to be measured the same way. We know that more background data is becoming commercially openly available as we speak. So there are more and more data sets we should consider to derive knowledge from, which we can then use for our fitness functions. Evidence-based decision-making, anyhow, is going to be the state-of-the-art approach. And large-scale developers or asset managers are already working on it. So now the question is, how can we, in our design community, foster this mindset also, too? Climate collapse, mass migration, and so on. I mean, those are going to be the dominant topics of our lifetime. Maybe not at the moment, but it's increasingly from year to year. So this is what we need to find solutions for, and this is what we need to find fitness functions for. In the same way with home office. I mean, the home office is here to stay. The same is with mobility as a service. I mean, in 20 years, hardly anyone is going to own a car because it's not necessary anymore. I mean, with fleets of self-driving cars or self-driving cabs, everybody can go anywhere, anyhow. So we have lots of space available, certainly in cities, because nobody needs a parking lot. And the processes are going to be tied together much closer. I mean, as I said at the very beginning, I mean, architectural competitions in near future are going to be designed Kaggle-like. And this is going to be a disruption, because architects are going to profit from it, investors and developers are going to profit from it, and in the end, tenants are going to profit from it. So this continuous flow of communication throughout the whole real estate domain is going to happen. And well, last but not least, as long as the interest rates are at the level as they are at the moment, I mean, there is an inflated real estate market. Maybe it's going to change with defaults in China, but this is more or less the situation we are in. So everything is highly volatile. Everything is going to be to change. So old experience, old rules are more or less obsolete very soon. So we need to foster a more data-driven fitness function environment very soon. So this was my talk. I hope there are a few questions.
Hello. Thank you very much for the presentation. There are a couple questions from me, but maybe we can answer those while we're waiting for the rest of the audience to. Oh, wait, I also just got a notification about one here. Okay, we can take this question from Limni first. Do you think we need to connect deep learning algorithms to actual sensors as a way for them to collect data in real time?
Yeah, this is something that's happening at the moment. So with this whole ESG discussion going on, I'm talking to some of the large asset managers who use smart meters throughout their buildings already in order to monitor the energy consumption. The issue is that existing thermal models they use on the building envelope are simply not accurate enough for a proper physical model. So when they did the thermal design, they underestimated certain clusters of functions within a building. And now with those sensors, they want to have a better understanding on how different complex effects are building up to power peaks. So this is something that is going to happen out of those sensors. Then they want to deduct certain design principles, which is difficult at best. So there's a really cool Swiss startup called Locketeer. What they do, for example, is they use Wi-Fi hotspots to track the movement of people within a building. And this is really useful for commercial real estate. But they were struggling at the moment to map those movement patterns to the design patterns they have in the apartments. So this is where these deep learning algorithms could, most probably shallow networks would be totally sufficient, could come up with explanations and with design proposals to improve this. So, Izzy, you also had a question.
Great. Yeah, I had a couple questions. I asked this in the middle, so you answered it a little bit, but I'll ask it again anyway, so we can get your full take on it. So we've moved away from rule-based to database paradigm, as you said. However, data is never just pure data. It can still contain a lot of biases based on who collected it and how. So in your view, how's the best way to take this into account when the biases are much less obvious in data than in human-based rules?
So the cool thing about bias is you can detect it algorithmically. So you need you don't find, you're not able, I mean, I would not be able to detect the bias. Maybe there are really good data engineers who can do this. But what we are using are simple statistics. So if you have proper target values, if you have proper variables, you can detect certain biases easier and can come up with explanations on the one hand and with countermeasures on the other hand. So what we have, for example, is an interface for architecture competitions. So what we do, so now we're talking about a design bias rather than a data bias. So in architecture competitions, we get the floor plans of the different competing designs. We then convert those floor plans into IFC files. We do our simulations, and then we do our analysis. And we conclude with certain box plots. So, for example, we detect that design A has much larger bathrooms in the 3-room apartments than all the other designs. Designer B has a much better design regarding evening sun in winter. So, for example, and it's more SWOT analysis. So we define the weaknesses and strengths of the different design proposals, or how architects are more or less designing. So because all the architects themselves anyhow have their own design process or their design patterns, as Alexander put it. So in this setup, we can now derive the design clusters. Mm-hmm. And what we can also do is we can correlate those design patterns with the rent revenue. So with the rent prediction, we know from the market the generic target group for such an apartment, what is it willing to pay for it? And would it be a penalty, a premium to have an increased size of a bathroom or to increase the sun exposure in the winter and evening? So we can then check if the bias or if the deviation from the generic solution space from each architect correlates with the market behavior, so it's a strength, or on the other hand, could be a weakness. So this is how data-driven you can mimic certain design principles. And this is also directly correlating to Wasame's question simply 3 minutes ago. So where he's asking how much evidence we need in order to have the groundwork to do evidence-based decision-making. And more or less you can start with roughly 1,000 buildings. So the moment you have 1,000 buildings and you know lots of stuff regarding those 1,000 buildings, you have resilient a resilient statistic. But under the assumption that those 1,000 buildings are more or less comparable, so that this is then status based, that you only compare small scale housing projects or medium scale offices, something like this. So it should be within one solution space. And then you can conclude already properly from it. But this is what I think all of those nice design groups, and there are really cool groups out there, I mean, from all those large scale architecture companies, if they would start revisiting their old designs, their old projects they did, start collecting additional data, and then do a little bit of research on these topics, I think their fitness functions would profit a lot from it. So I think we have time for one more question. Anyone up for it?
Yeah, we have a last audience question here. What about combining rule-based and database optimizations? For example, adding weight/importance to KPIs. And what is your opinion on AEC ontologies, rule-based ontologies, and would they assist in the design process?
Yeah, good question. So first of all, yeah, combination is always okay. So I mean, everybody is combining rule-based and data-based. Everybody should combine rule-based and data-based information. The issue is only if you miss on the database stuff, you simply miss on more accurate and more up-to-date knowledge. The other one is much more interesting because those ontologies themselves are an issue for me. And when we are now talking about, and of course, we always need to have certain ontologies in order to have nice interfaces. I mean, we are now computer scientists more or less, so we're working with APIs, REST APIs whatsoever, or we work with Speckle. So we have certain definitions we need to work with. And I think it's a good common ground. But now there are other startups trying to come up with a substitute for these ontologies, like what language models themselves are doing, like Google Translator. So what Google did is, Google is not translating German into English. Google is not translating Chinese into Portuguese. Google is translating every language into a Google model, and from the Google model back to the other language. And I think this is the same what we now need to consider for AEC. So I think there are going to be different patterns, different standards, different ontologies. There is going to be a machine learning AI interface somehow in between, which is able to understand the patterns most of the time based on their geometrical representation. And then out of this, translating this information into other formats again. So, I mean, we ourselves do the same thing. For example, when we import an RFC file, when we import a PDF, when we import a DXF file, we redraw. So we understand the geometries, we understand the patterns, we understand the ontology of the parts. We put our own Archilyse pattern on top of it. We are rebuilding everything. And then we're exporting back into the same formats. We can give you a nice IFC file, we can give you another PDF, another DXF or DWG. So it is just that we have this more or less standardized ontology in between, and this standardized ontology is data-driven, meaning it can develop continuously. So if new elements arrive, we simply increase the ontology. So the ontology is always built on the fly. These predefined ontologies are a big hassle. I mean, these big predefined ontologies are like the search engines from the 1990s, like AltaVista, Yahoo, where you had everything categorized. And this doesn't work out. You need to have something much more leaner, much more agile on the fly. And this is going to happen.
Great. Thank you so much for this. I think we are out of time, but thank you again, Matthias, for the great and the lovely conversation afterward.
Thank you, Isa, and thanks for the invitation. So, bye, everybody.
Thank you so much. Goodbye.